Exploring the future of learning with digital technologies. That's the strapline of the London Knowledge Lab. And people often ask me, well, why the Knowledge Lab? Why not the Learning Lab or the Teaching Lab? And the answer is, we teach and expect pupils to learn a very tiny little fragment, almost like a sliver of mathematics at the moment. And that sliver of mathematics has been decided, not completely arbitrarily, but about what it is really reasonably possible for students to learn if they don't have a computer. And I want to just answer the question, why the Knowledge Lab in the context of the Cornerstone project, because I think there's a link up that I'd like you to make. The point is this: is the role of technology, or indeed the role of education, just to do better what we've always done? Is there really so little change in what there is to be learned that we want to maintain as an invariant, if you like, what it is that we're trying to set out to teach? Or are there really things that we couldn't teach before? Can we really make ideas learnable that were not learnable by ordinary people? They were always learnable by some special people who become mathematicians. But in general, mathematics is a very, very hard subject. And one of the reasons why it's a very hard subject is that you can't, as Andrew said in the video, touch and feel it. It's a very abstract subject. And so the question becomes not how do we do better, how do we do a better job of teaching what we always used to teach, but what is it that we can now teach in ways that were impossible before? How can we change the knowledge that we are making available for people to learn? So let me give you the example that you've already seen, but you haven't seen it in the context of new knowledge. You saw in the video that in studying what a graph is, you actually pull the graph with your finger, if you're using an iPad, for example. You actually pull the graph into different configurations and make something different happen on the screen. If you don't have a screen, if you don't have a computer, all you can reasonably do is think abstractly about what the motion is, maybe write some equations, and then draw the graph. But if you get the graph wrong, well, nothing's going to happen to you. The motion will stay the same. The algebra will stay the same. There is no feedback. There is no dynamic link. So in making the graph something that you can touch and feel and something that really affects the phenomenon that you're looking at is a new kind of knowledge. Not having the computer is like trying to learn about music without having a musical instrument to play, like learning the piano without having a piano. It can be done. And there are people who are really accomplished at hearing the music without a musical instrument. They're so special that we call them musicians, just like we call mathematicians mathematicians. I'm going to give you one last example of this new kind of knowledge that it's possible to think about. We've just finished a 5-year project on trying to get people to understand what algebra is all about. And what algebra is really all about is the amazing fact that you can find out that 2 odd numbers always become an even number without going to infinity and beyond. You can find out that there really have to be an infinite number of prime numbers, and you can prove that in 3 lines of algebra. It isn't only about being able to move algebraic symbols across the equal sign and learn how to manipulate, although that is a vital skill. So our project was based on the understanding that algebra isn't a very good way to learn algebra. That's to say, playing with the letters of algebra is not the only way to learn what the big idea of algebra is really about. And what that big idea is about is proving that things are true even if you can't go and stand at the end point to see if they've always been true. In order to do that, in order to help people access that new kind of knowledge, for which I mean that kind of knowledge that really only mathematicians feel comfortable with, we had to build a new language, a kind of quasi-algebra. It kind of looks a little bit like standard algebra, but it's much more learnable. And why is it learnable? Because it's dynamic, because you can You can move things with your fingers and see what the algebraic effect of them are. Crucially, you build things and then express them in this pseudo quasi-algebraic language that we've developed. And that forced us to try to understand and make explicit to ourselves, what is this new kind of knowledge that we can build with computers? The really exciting thing for us in Cornerstone is not just that we're using computers. There are many, many really established and beautiful systems for doing mathematics with computers. But what really makes a difference to us is that for the first time in 30 years of research on mathematics learning, I'm finding real teachers and real students learning mathematics at scale. And for us, that's a really exciting prospect. Thank you.